Hey everyone, in this video we're looking at type 1 and type 2 errors in hypothesis testing. I want to start with just a little introduction. I have a couple of example claims so that we can talk about what the null hypothesis is. If you're already familiar with hypothesis testing, you can jump forward in the video. So my first example, it says, according to a National Ski Areas Association survey from 2023, 90% of skiers and snowboarders wear helmets. And I want to know, do skiers and snowboarders in Colorado wear helmets more frequently than this national average? So I'm looking at a population of Colorado skiers and snowboarders, and I want to know essentially what percentage of them wear helmets. So we could determine this by doing some sort of sample and measuring the proportion of the sample. But the claim that I'm making here would be about the population. In this case, I'm making a claim about a population proportion. So my claim here might be something like P greater than 0.9. I'm stating that the proportion of all Colorado skiers and snowboarders that wear helmets is greater than 90%. Now that may or may not be true. We need to collect some data to determine whether that's true or not. And when we do hypothesis testing, we have a hypothesis like this, that P is greater than 0.9. And then we also have the null hypothesis, which is sort of, it's generally the opposite of whatever we're trying to claim. The null hypothesis here would be P equals 0.9. In this case, this is saying that there's essentially no difference between Colorado skiers and snowboarders and the national average. So the null hypothesis is always sort of no change, no effect, no difference, something along those lines. It's always going to be an equal statement, and this could be for a proportion or a mean, some sort of population parameter. And depending upon what type of claim we're making, we'll do some different calculations. So here's one more example claim. We're told in the summer of 2024, CDOT's I-70 traffic data showed a mean commute from Silverthorne to C-470 on Sunday afternoons was 92 minutes. This is just an estimate. I wasn't able to pull the true traffic data, but we're just assuming that that was the case in 2024. And CDOT wants to know if the new Mountain Express lane change changed this mean travel time in the summer of 2025. So if we look at mean travel times in 2025, are they going to be any different from what they were in 2024? This is a claim about a population mean rather than a proportion. So my claim is going to be some statement about mu, the population mean. In this case, this is the mean of the travel times. And I'm comparing it to 92 minutes. The claim I'm making here is that the mean is different from 92 minutes. Ideally, the addition of the change in the express lane would decrease the mean time, but the claim here we're just making is that it's something different, right? Maybe it got higher, maybe it got lower. We're leaving both of those possibilities open. So our claim here is that mu is not 92. The null hypothesis, again, is going to be an equal statement, and in this case, that would be that mu equals 92, meaning that there was no change in adding that new express lane. The mean commute time in that range is still just the same. There's definitely other types of claims you could make with this particular data. You could do a claim about the difference between two population means. You could claim that the mean was specifically less than 92, but this is just the example that I'm working with here. So with either of these hypotheses, the next step in the hypothesis testing process would be to collect some actual sample data so that we can make a judgment about whether our claims are true or not. And for either one of these, let's say we're looking at the claim that mu is not 92. What we're going to do is we're going to assume that the null hypothesis is true. In this case, we're assuming that the mean commute time in 2025 is the same as what it was before, is just 92. Then we're going to look at our sample data and we're going to see how how likely is that, right? So how far off is our sample data from this assumption? So if we assumed that the mean commute time was 92, but when we took our sample, the sample mean was, 170 or something drastically different, then that would be strong evidence to conclude that our null hypothesis was not true, right? So we're basically looking at the sample data and seeing how far off, how unlikely is that data if the null hypothesis was true. And if it is significantly unlikely, meaning that we're getting a mean that's much higher than 92 or much lower than 92 when we look at our sample data, then we would reject the null hypothesis. In contrast, if the sample mean that we got was fairly close to 92, it doesn't have to be exactly 92, but if it was pretty close, then we would fail to reject the null hypothesis and just say, well, it seems like the null hypothesis could be true. Notice that we're failing to reject it. We're not saying the null hypothesis is true. We're just saying that essentially the sample data wasn't different enough to conclude the null hypothesis was false. So every hypothesis test is going to have a conclusion something like this. So depending upon what we see in the sample data, we're either going to reject the null or we're going to fail to reject the null. So this brings us to our type 1 and 2 errors. So here's a summary table of what type 1 and 2 errors are. The type 1 and 2 errors are basically the two different ways we could be incorrect in a hypothesis test. So let's think again about that first claim. The claim was that P was greater than 0.9, meaning the proportion of Colorado skiers and snowboarders that wore a helmet was more than 90%. And the null hypothesis was that P equals 0.9. So we have two possible truths out there. Either the null hypothesis is true or the null hypothesis is false. The null hypothesis is false would mean that P is in fact greater than 0.9, that the claim is in fact true. The null being true would be that P equals 0.9. We're excluding the P less than 0.9 here, but if it was less than 0.9, that would fall into the null category. If your sample data showed a value less than 0.9, then we definitely don't think that this claim is true. But if the null hypothesis is false, that would mean that our claim is true. If the null hypothesis is true, that would mean that our claim is false. So if we're in the reality that Colorado skiers and snowboarders do in fact wear their helmets more than 90% of the time, we have two possible conclusions. Either we rejected the null hypothesis when we did our hypothesis testing, in which case we made the correct decision, or we failed to reject the null hypothesis, meaning that we said that the evidence wasn't strong enough to conclude that more than 90% of the skiers and snowboarders in Colorado wear their helmet. So we failed to reject the null hypothesis. We failed to support this claim. This is an incorrect conclusion if it's true that P is greater than 0.9, and this would be called a type 2 error. In contrast, if the reality is that Colorado skiers and snowboarders don't wear their helmet more than the national average, so the null hypothesis is true, then the incorrect conclusion would be to reject the null hypothesis. So if we rejected the null hypothesis because our sample data seemed to indicate that P was greater than 0.9, so our sample data showed a higher p-value, this would lead us to the wrong conclusion. We would get a type 1 error. So type 1 errors are when we reject the null hypothesis incorrectly, or incorrectly with what we should have concluded based on the true population value. And then type 2 errors are when we fail to reject the null hypothesis incorrectly. This is often explained with an analogy with the US justice system, where we have the assumption of innocent until proven guilty. So in that hypothesis testing diagram, we have our H0 is essentially assuming innocence. And then we only reject that null hypothesis if the jury finds enough evidence to do so. So we look at the evidence in court, and if we reject the null hypothesis, that would mean that you rule that the person is guilty, or you convict them. And then if there's not enough evidence, then we just assume that the person is innocent, and that would be when you acquit. So rejecting the null would be equivalent to convicting the person. Failing to reject the null would be equivalent to acquitting that person. And in this case, the evidence presented would be essentially like your sample results. So again, we have 2 or 4 possible conclusions here. Either we have an innocent person and we convict them. This would be a type 1 error. This is where you convict someone who should not have been convicted, a wrongful conviction. Or you have an innocent person who is acquitted. That would be a correct outcome. Or if we have someone who actually did do whatever they're accused of, we can either convict them, which would be the correct decision, or if we acquitted the person who did in fact do the crime, that would be equivalent to a type 2 error. So in this analogy, the type 1 error is convicting an innocent person. The type 2 error is acquitting a person who is actually guilty. In any justice system and in any hypothesis tests, you can never completely eliminate the possibility of type 1 and type 2 errors. Because of the randomness involved in sampling, there's always going to be some possibility that our sample does not quite correctly represent the population. And in the jury system, maybe there's just not enough evidence, or maybe there's some evidence that was incorrect and we don't realize it. There's always some chance of errors. What's important about the type 1 and type 2 errors is that in some cases, one of these errors might be much more harmful than another. So in the US justice system, we have mostly concluded that convicting an innocent person is worse than failing to convict a guilty person in most cases. And so we kind of lean towards requiring stronger evidence to convict someone, even though that means, you might sometimes let somebody go who's guilty. We want to minimize both of them, but considering type 1 and type 2 errors can help us construct our hypothesis tests correctly. And just to sum up, we are going to get into the details of hypothesis testing as we move forward, but when we look at type 1 errors, the probability of a type 1 error is alpha, which is the significance level, and this is something that we choose. So if you've already seen confidence intervals, when we choose that confidence level, like 95%, 99%, this is the same kind of thing for hypothesis testing. So the smaller we make our significance level, the less likely a type 1 error is. So if we want to require very, very strong evidence, we can make our significance level very small, and the probability of making a type 1 error will go down. However, if you make your significance level lower, then the probability of a type 2 error goes up. So there's kind of a trade-off here. And the same is true for our justice system analogy. So the stronger you make your requirement for evidence, or the tinier your significance level, the more likely you are to make a type 2 error. So you generally need to try and find a balance between those two. The most common significance level in hypothesis testing is 0.05. So sort of a 5% error rate. That would be that type 1 error rate. The probability of a type 2 error is a little bit more complicated to calculate, and it's not something that we're going to get into in this class. But it's important to realize that there is this trade-off. If alpha is lower, beta is going to be higher if everything else is equal. One way to reduce the probability of a type 2 error without changing the significance level is to use a bigger sample size. So using a larger sample is always generally a good idea, at least up to a point. It will make our results more reliable. That's it for this video. Thank you for watching.